Hi everyone, in this video we're going to go through section 1.7 titled Linear Independence, and in this section we take a look back at homogeneous equations. That was our system that was all equal to 0, and take a look at them from a different perspective. Okay, so we're looking at them more as vector equations, as you can see at the top here. We have a vector equation that is a homogeneous system. And we know, because it's homogeneous, that by inspection, just by looking at it, we know that the trivial solution exists. The real question, as it was in 1.5, is whether a non-trivial solution exists. Is the trivial one the only one? Okay, so we're still looking at it with that same lens, but shifting our perspective, focusing more on the vectors themselves. So our definition here, we have an index set of vectors, v1 through vp, is said to be linearly independent if this vector equation, x1 v1 plus x2 v2, etc., is equals 0, has only the trivial solution. So if only the trivial solution exists, then that set of vectors is called linearly independent. And then to contrast that, it is the set of vectors is linearly dependent if we can find weights c1 through cp that are not all 0, so that this equation is still equal to 0. That linear combination is still equal to 0. So if a non-trivial solution exists. Now let's look further at that definition. In this first example, we have v1 is 1, 2, 3, v2 is 4, 5, 6, v3, 2, 1, 0. First question, is that set linearly independent? And if you're wondering procedurally, what do we do here? Well, lo and behold, the first step is to write a matrix, 1, 2, 3, 4, 5, 6. You can choose to augment this with a column of zeros or not. That is entirely up to you. Actually, you know what? I'm going to for now. At some point, I won't, but I am going to keep my column of zeros for this example. And then we're going to do some row operations and see what we get here. I'm going to jump right to the end. It looks like this: 1, 0, negative 2, 0. Let's see, 0, 1, 1, 0. And then we have a row of zeros. So to answer the question, is this set linearly independent? The answer is no, it is not linearly independent. NT. It is linearly dependent. Okay, so to clarify, linearly independent means only the trivial solution exists. We would have a 1 in this position if only the trivial solution exists. Linearly dependent means we have a non-trivial solution because we have a row of zeros here. We do, in fact, have a non-trivial solution to this system. Now, part B says, if possible, find a linear dependence relation among those three vectors. What we do is we take our free variable, which is the one that's missing a pivot, and we're going to choose x3 is equal to 2. That is my choice. Actually, I wrote it down when I took my notes out of the text, but you are free to choose any number for x3. That is why it is a free variable. Okay, if x3 is equal to 2, then x1 is equal to 4, x2 is equal to negative 2, and x3 is equal to 2. So those are my three solutions, my three values in this non-trivial solution, and then we can substitute them in as a linear combination with that vector, the three vectors up above. 4 times v1 minus 2 times v2 plus 2 times v3 equals 0. The 4, the negative 2, and the positive 2 came from right there. And that's the end of that example. This next slide just clarifies that just like we can talk about the linear independence of a set of vectors, we can also write them as columns within a matrix and talk about the linear independence of the columns of a matrix. So what it says in the gray box here, the columns of matrix A are linearly independent if and only if AX equals 0 has only the trivial solution. So if I only get the trivial solution, then my columns are linearly independent, just like the vectors in the last example. So we can talk about columns of a matrix or vectors in a set. In our next example, we have just that, a matrix, and we want to know if the columns of this matrix are linearly independent. So same exact steps as before, 0, 1, 5, 1, 2, 8, 4, minus 1, 0. Augment that with a column of zeros representing that homogeneous system. And then, all right, let's see, that is row equivalent to 1, 2, negative 1, 0, 0, 1, 4, 0, and 0, 0, 13, 0. And as you're going through these row operations, as soon as you identify that third pivot for our 3 by 3 matrix, we know that the columns are linearly independent. We could go further with our row operations, and you would end up with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. You would end up with an identity like that, but there's no need. As soon as you identify the third pivot in your 3 by 3 matrix, you're good to go. You can stop there and say, all right, now I know that my columns are linearly independent. We'll first look at the linear independence of sets of either just 1 or 2 vectors. And what it says here to start out with, if I have just one vector v, that set, a set of one thing, of one vector, is linearly independent if and only if v is not the 0 vector. So give me any vector that you want that doesn't consist all of zeros. Let's say 1, 2, 3, 4. A 4 by 1 vector. If that is the whole set, those are supposed to be little squiggly brackets, maybe, that set is linearly independent because x1 times v equals 0 has only the trivial solution. The only way to have a scalar, let me write this down, a scalar x1 times 1, 2, 3, 4 equals 0. The only way for that to work is when that scalar is in fact 0. So that set is linearly independent, but if I'm talking about the 0 vector, that set is always linearly dependent. So if I have a set consisting of the 0 vector and only the 0 vector, that set is linearly independent, linearly dependent, because x1 times that vector, that's 0 at the bottom, equals 0, has lots of non-trivial solutions. x1 can take on any value that it wants. So that's specifically looking at just a set containing one vector. The next slide we'll look at a set containing 2 vectors. Now, if I only have 2 vectors, you can tell pretty quickly whether they are linearly independent, okay? And that is done by inspection, by looking at the 2 vectors. If you notice, to go from v1 to v2 in A, you double v1 and you get v2, right? That's something that with 2 vectors I can fairly quickly identify. So I know that negative 2v1 plus v2 is equal to 0. I have a non-trivial solution. Negative 2 and 1 are the weights that satisfy this system. 0 and 0 satisfy the system. We know that, though. Negative 2 and 1 is another solution. So that means that that one is linearly, I'm going to abbreviate here, dependent. Whereas with the next one, there's no scalar to get from 3, 2 to 6, 2. I can't use any scalar to get from one to the other, so that set is linear, that's an arrow, is linearly independent. Linearly independent, okay? And so when we only are looking at 2 vectors, all we have to figure out is, do they scale each other? If the answer is yes, they're linearly dependent. If the answer is no, they're linearly independent. Once you have more than 2 vectors, then you're going to a matrix and doing row operations. Now we come to a theorem where we characterize linearly dependent sets. And if I have a set of vectors v1 through vp, and there are two or more vectors that are linearly dependent, right? That set that set is linearly dependent if and only if at least one of the vectors in that set is a linear combination of the others. So a linearly dependent set, I can write one vector in the set in terms of, as a linear combination of, the other vectors. Okay, and it says, in fact, if S is linearly dependent and v1, the first vector in the set, is not the zero vector, then there is some vector vj later on in the set that is a linear combination of all the preceding vectors, the ones that came before it in the list. Okay, so that's linearly dependent set means I can write one of the vectors in the set as a combination of the others. In our next example, we're given two vectors u and v, 3, 1, 0, 1, 6, 0. Question says to describe the set spanned by u and v, so what does the span, the set of linear combinations of u and v, look like, and explain why a vector w is in the span of u and v if and only if the set u, v, w is linearly dependent. Okay, so a couple things to do here, including talk about what if and only if means if you're not familiar. All right, so first, the set spanned by u and v. Okay, first you ask, how many vectors are there? The answer's 2. I can see them. Then what do I need to note about those two vectors? Well, the important thing to note about those two vectors is that they are not multiples of each other. Each, too close together there. Other. Those two vectors are not multiples of each other, so they are linearly independent and they span a plane in R3. Okay, how do I know that? That's not the best R I've ever made, but we'll go with it. How do I know that? Right? They exist in 3 dimensions because they have 3 entries. One vector, the span of that is a line in R3. 2 vectors, as long as they don't scale each other, the span of that is a plane in R3. Okay? 3 vectors that are linearly independent would generate all of R3. So that's the answer to the first part. There, that set it spans a plane in R3. To think of that in a more visual way, right? See how well I can draw here. The vector u, let's say that u is right there, and let's throw the vector v somewhere over there, right? Their span would be a plane in R3. Let's see if I can just draw this, right? And it would continue on in all in positive and negative directions, but I'm just drawing it kind of as a rectangle here. That plane continues outward, but it follows the path that u and v are on, the plane that u and v are on. Now the next thing that we have to do is to explain why a vector w, so if we introduce a third vector, when it's in the span of uv, then it has to be, uvw has to be linearly dependent. Okay, and so there's this if and only if here. And what that means, okay, what we have to show, with this problem, is that w is in the span, let me just kind of break this apart a little bit. W is in the span of uv, u comma v, that means that UVW is linearly dependent. And then we'll have to flip that around. We have to show that UVW is linearly dependent means that W is in the span. So we have 2 more steps here. This is a kind of lengthier problem, but it's introducing us to how we write a proof in math. Okay, so this may be new for some of you. The rest of this problem is wordy. I encourage you to listen and take some notes and really try to understand the logical connections, okay, because that's what this is. If and only if is a logical connector, and what it does is say, how do I go from this clause to that clause? When they're connected with an if and only if, one implies the other, and backwards also works. Okay, so if that was a little bit confusing, that's fine. We'll now go through the actual how-to of the problem. Okay, and what we do is we start out, well, the how-to of the proof is we start out with this, and we're going to say if W is in the span of U comma V, then what does that mean? It means it is a linear combination of U and V. Linear combination of U and V. Okay, that's what it means to be in the span. Now where we go from there is we can now say then the set UVW, U comma V comma W, is linearly dependent. That's what we want to be able to say. D-E-P-E-N-D-E-N-T. Linearly dependent by theorem 7. That was the theorem from the last slide that said that a set of two or more vectors is linearly dependent if and only if at least one is a linear combination of the others. And that's what we have. W is a linear combination of U and V. So we have exactly what is described in Theorem 7. So we've got, this is called the forward direction of the proof, okay, which is often a little bit shorter and a little bit easier to understand sometimes. Maybe not in this case because the first time we're doing this. But the next step is in what we need to show here is, can we do this in the reverse order? If I have U, V, and W are linearly dependent, can I then show that W is in the span of U and V? Okay, and let's go through how we do that. All right, and we start out with the beginning part of this if-then statement. Again, if the set UVW, if UVW, sometimes a little bit of proof writing seems redundant at times, meaning you're writing the same thing over and over. That happens. But if that set, if they are linearly dependent, then Theorem 7, so we're using Theorem 7 again, says some vector in the set U comma V comma W is a linear combination of the other vectors. Okay, now here's the important part. It must be W. It must be W. And I want you to pause the video here. Well, you can if you want to. Pause the video here. See if you can decide why it must be W. Okay, but the reason that it must be W is because since V is not a multiple of U, we know that they are linearly independent. Those two vectors are, so the one that's dependent has to be W. Okay, then that gives us our conclusion. W is in the span of U and V. Okay, those are squiggly brackets again. That's the end of the problem. A little bit longer and a little bit deeper in terms of understanding the theory. Okay, read through it in the text. This is similar to what you'll read in the text, but there's less audio when you read the textbook. The goal in this course is to understand both the computational linear algebra as well as the theory that we investigate. Theorem 8, I'll read for you. You can read it on your own, pause the video, but I'm going to leave it to you to think about why, or you can probably read it in your textbook, but figure out why this theorem hopefully makes sense. If a set contains more vectors than there are entries in each vector, the set is linearly dependent. Okay? If there are more vectors than entries, the set has to be linearly dependent. Here's an example using Theorem 8 from the last slide. If I have these three vectors, they are linearly dependent by Theorem 8 because there are three vectors in the set, only two entries in each vector. Notice, however, that none of the vectors is a multiple of the other, right? So 2, 1, 4, -1, -2, 2. No one vector is a multiple of the other, but because we have more vectors than entries, they're guaranteed to be linearly dependent, right? Those three vectors in R2 would exist on the same plane, right? If I added in a third entry, now I'm not writing zeros, I'm circling an imaginary third entry, then those three vectors wouldn't have to exist on the same plane. They might be in different planes in R3. The next theorem, again, I'll read it for you, but I encourage you to think about or read your book to figure out why this theorem hopefully makes sense, or why it should make sense. If I have a set of vectors that contains the zero vector, that set is always linearly dependent. So write out an example. Give yourself a few vectors. Why does that set, if it contains the zero vector, why does it have to be linearly dependent? Again, that's a good question to try to think about and figure out. We'll close out the section with example 6, determined by inspection. That means by looking, without doing any actual computation, if the given set is linearly dependent. Okay, pause the video if you want to try to decide for yourself for each one. Part A is linearly dependent, right? Why is it linearly dependent? We have 4 vectors with 3 entries in each, right? That is Theorem 8. Theorem 8. Theorem 8 says if you have more vectors than entries, linearly dependent. Letter B, that is also linearly dependent. For this one, I'm looking at Theorem 9. Theorem 9 says if it contains the zero vector, there it is, then the set is linearly dependent. Letter C, take a look at it for a minute. It almost looks like the second one scales the first one to go from a 2 to a 3, multiply by 3 halves, but it's -3 halves. This one, -3 halves, gives me that number. This one, -3 halves, gives me that number. That one, -3 halves, comes oh so close to that number, but not quite there. So 3 of them work. This one's a fail. So this set, because the vectors don't scale each other, that set is linearly independent. And the only time that I can use scalars as a reason for linear independence is if I only have 2 vectors. That's the only time that argument can apply. All right, that is the end of 1.7. Thank you very much for listening and have a wonderful day.